Should be like that, no?
Yeah, it should be like that, but unfortunately they swapped the monitor, so it's okay for me, no problem. So just give a minute and we can start.
Okay.
Okay, I think I will start now, and let's see if it works, the video. So we go with the video. So good afternoon. On behalf of the organizing committee, I take the pleasure in opening the CryoSat 10th anniversary science conference and convey my personal and earthly welcome to the opening speakers and to all the participants from all over the world who are attending and contributing to this event. So good morning also to our American colleagues and good evening to our Asian colleagues. Let me introduce Jérôme Buffard, who will co-chair this opening session with me. The conference, as you know, was originally planned to be held in Taormina in Sicily, which is considered the cradle of the European culture and the home of many leading scientists in classical Greek period. Let me just remind you Archimedes from Syracuse, not far from Taormina, who is considered not only to be a great mathematician, but also a great physicist. He was the scientist who discovered the law of buoyancy, which is now today used in our algorithms to calculate the sea ice thickness. And Empedocles from Agrigas was the first scientist to have divided the natural elements in 4 categories. I must admit that when we initially feared that owing to this virtual format, there would have been, I would say, less motivation to attend, but we were wrong. When we opened the call of abstract, we received many more papers, which forced us to reshape the program and made the selection more difficult for us. I have been told that now we are about 260 people who have registered to the event. This shows that there's still a lot of captivation and enormous interest of the CryoSat mission, even after 11 years in space, because this mission has been a scientific and a technological inspiration for many other missions which are flying today and will hopefully fly in the near future. For this reason, I very much look forward to hearing the new scientific results and discussing which will be important to shape our mission operations the next 3 years. Let me take the opportunity to remind you not to forget to redeem your code to plant our trees in ESRIN, which is called the Forest Space for Trees, which is physically placed in Kenya. Each registered participant should have received 2 codes. This is if you want, a small initiative to try to mitigate the CO2 footprint as a result of this conference. And finally, on behalf of the organizing committee and of the CryoSat team, it is my great pleasure to invite my director, Tony Tolkel-Nielsen, on this virtual stage for his welcome address. Tony, the floor is yours.
Thank you very much, Tommaso. Ladies and gentlemen, dear colleagues and friends, it gives me a great pleasure to take part in the opening of the CryoSat 10th Anniversary Science Conference, and I'm pleased to welcome you all. It is high time that such an event takes place to highlight the remarkable contribution of CryoSat. My sincere thanks goes to all of you who generously helped us make this event come together and to become a success, that I'm sure it will be. Last April in 21 saw the 11th anniversary of ESA's CryoSat 2 satellite in orbit. CryoSat's original remit was to measure variations in the height of the Earth's ice and to reveal how global warming is affecting the polar regions. CryoSat has been instrumental in mapping changes in the thickness and volume of Arctic sea ice, which plays a central role in the global climate system as it reflects solar radiation back into space, and because it moderates ocean heat transport around the planet by insulating the relatively warm water from the cold polar air. In addition, CryoSat has also determined the contribution that the Arctic and Greenland ice sheets are making to the mean global rise in sea level. It should be added that CryoSat has led to a wealth of scientific discoveries that go far beyond its primary objectives. A glance through the list of presentations planned for the next few days reveals the amazing diversity of these applications. While the conference focuses on the latest scientific results from the mission, it is also a celebration of the remarkable long-term contribution CryoSat has made to our understanding of the cryosphere and its role in the Earth system and the climate, and in turn the impact on society. CryoSat has for more than 10 years been a valuable source of data for oceanography, hydrology, and geodesy. Data of CryoSat 2 have underpinned the importance of long-term records and ESA's commitment to preserve and achieve this through its programs and international collaboration, including our partners in the EC and EUMETSAT. CryoSat has also highlighted the role of ESA and especially Earth observation in developing new satellites, missions, and observation techniques to address scientific challenges. These are what we call our Earth explorers, and also to address societal and policy demands. As you know, ESA is responding to these challenges following a science user-driven approach and accounting for societal and political priorities also, among others in the context of the Sustainable Development Goals and UN environmental conventions like the COP21. In addition, I would like to highlight that CryoSat's technical advancements have also paved the way for the future altimetric missions built in partnership with the European Commission, including Sentinel-3, Sentinel-6 Michael Freilich, and the future Crystal mission. CryoSat is a cool satellite, funded as part of the ESA's EOP Future EO program. ESA's Future EO includes dedicated elements to advance Earth system science as a tool to develop new solutions for society. As it is not enough to use Earth observation only to advance our understanding about our planet and its subsystems, such increased knowledge needs to be translated into solutions and services for citizens in Europe and worldwide. The CryoSat 10th Anniversary Conference provides a forum for international scientists and operational users to present and share state-of-the-art CryoSat-based results, its decadal contribution to science and future perspectives. I would like to thank take this opportunity to thank the ESO CryoSat project and industry teams that built this remarkable mission. In addition, allow me to extend my gratitude to the ESA mission operation team, which has operated and will look after this important European asset well beyond its originally planned lifetime. This has been also possible thanks to the support of the scientific international community, to whom my appreciation goes today. Ladies and gentlemen, conferences such as this provide a valuable opportunity for research scientists, specialists, and decision makers to share experiences and to look forward to the future. As to today, the performances of CryoSat satellite remains well above the design specification. Overall, the satellite space segment are performing nominally, and I touch wood, we should be able to profit from CryoSat for years to come. I'm grateful to the many experts who have come to share their knowledge this week. I especially welcome the Director General of ECMWF, Dr. Florence Rabier, the EU Special Convoy for Arctic Matters, Mr. Michael Mann, Dr. Sovi Nowicki from University of Buffalo, Professor Andrew Shepard, Principal Scientist of the CryoSat mission, and all other participants from national and international organizations, representatives from governments and scientific institutions who have joined us. I'm sure you will have a fruitful and rewarding exchange in the coming days. I wish you every success with this important conference, and I look forward to learning about the outcome. Thank you very much for your attention.
Thank you very much, Tony, for this welcome speech, and good afternoon to everyone. So now we will let the floor to Dr. Florence Rabier, who will present a paper on the importance of observing Arctic for weather forecasting and climate monitoring. Dr. Rabier is the Director General of ESA-ESRIN since January 2016, and a well-known international expert within the meteorological community for her key role in developing innovative data simulation techniques from Earth observation satellite. During her career, Florence has also demonstrated a particular interest in the area of CryoSat-related sciences, leading a major field campaign over Antarctica in the context of the International Polar Year. So please, Florence, the floor is yours. You can share your screen.
Okay, thank you very much. I'm going to share now. Okay, so sorry. So yeah, the title of this talk is a bit broader than just CryoSat, because it's about observing the Arctic for weather forecasting and climate monitoring, which is what we do in particular at ECMWF, the European Centre for Medium Range Weather Forecast, together with partners. So why the Arctic? Why is the Arctic important? So in numerical weather prediction, we have made some progress quite steadily in the last decades. So we say that every 10 years, we win one day, we gain one day of predictability, which is 10 years ago, maybe we could predict the weather up to 7 days ahead, but now we can predict it up to 8 days ahead. So every decade, we win one day of predictability. This is also the case in the Arctic, actually, where we also progress steadily, except that the performance is much poorer in the Arctic, both for analyzing the Earth system and predicting the Earth system. It is more complicated in the polar areas, and in particular the Arctic. So what we use for doing this weather forecasting and monitoring is an Earth system. So we are developing the science and the tools for it. What do we call an Earth system? Well, this is what is represented here, which is the composite of the atmosphere, the ocean, the land, the sea ice. And what we are doing is actually we are coupling all these components of the Earth system in our forecasts from all forecast ranges to predict the weather for 2 days ahead up to a few seasons. All our forecasts are fully coupled between all these different components. And to start with, of course, we need to analyze what's going on. And So to capture the state of the Earth system, we use around 800 million daily observations coming from all sorts, including more than 95% of them come from satellites. So before going to the Arctic, just in broad terms, how do we use CryoSat more globally in our global model? Because what we do at ECMWF is doing predicting the weather or analyzing the state of the atmosphere over the whole globe. So we use CryoSat for ocean analysis. This is a picture of sea level anomaly, the departures between a short-range forecast and the data. So when you see light yellow colors, it means that they were quite aligned. When you see darker colors, like in the Gulf Stream or Kuroshio currents, that's when a lot of things happen, a lot of eddies, and so it's a bit more difficult to be fully aligned. And for our models, our ocean model is only 1/4 degree resolution, so it's more difficult to capture this small-scale variability. Nevertheless, we use the data on a routine basis. We also use CryoSat globally for analyzing wind and waves. We use different products, and so then we have surface wind speed and significant wave height in the end as products, as parameters, which we analyze. These are just some scatter plots between the data of CryoSat 2 and the ECMWF model. You have the surface wind speed on the left and the significant wave height on the right, and you see the model parameters of on the x-axis and the satellite parameters on the y-axis. As you can see, we are quite aligned along the diagonal, which means that we have quite a good agreement between the observations and the model, which makes it even easier to then use properly the information from the data. This is just an example of the mean impact on the significant wave height field of using CryoSat 2. So this was for 10 days a few years ago, but it's just to show an illustration how it actually changes the mean wave height field. And also in terms of forecast quality, it was shown that CryoSat 2 on top of another altimeter still gains some benefits in terms of forecasts for our significant wave height forecasts. Now, we also produce, at ECMWF, we are running the Copernicus Climate Change Service on behalf of the European Union. And in our activity, one of our main activities is to produce these reanalyses of the atmosphere going back decades ago. In particular, a few months ago, in April, we published the European State of the Climate for 2020. So typically every spring, we go back to the previous year and we do a sort of summary of what happened in the world, and in particular with a focus over Europe. So what was special in 2020? Well, it was a warm year. But if you make a zoom towards the Arctic, this was a very special year for the Arctic. In particular, when you see on the top left plot here, you can see that this was the second warmest year on record in the Arctic, with 2.2 degrees more than the average of the 30-year running average. So quite a significant warm year, a second warmest year. So when I say 2.2 degrees more than average over the Arctic, actually locally in Siberia, we had more than 6 degrees over the whole year, more than average. This is just the largest ever departure from the climatology anywhere on Earth. So this shows really the importance of the Arctic and in the polar region in general. So this translated in the second minimum sea ice extent after 2012, in September 2020, and the largest ever total annual carbon emissions from wildfires in Arctic Siberia. We had huge amount of fires, and you can see through June, July, August, a huge amount of carbon being released in the air, which is quite dramatic, of course, for the Arctic, but for all of us anywhere else on the planet as well. So the Arctic is such an important area that actually we are also running a regional reanalysis in the Arctic, actually on 2 different domains. So these are not run at ECMWF, but they are run in particular. Met Norway is leading some of them, together with the Nordic countries. So why is it interesting to do a reanalysis a bit more local? Because you can use more resolution in the models we're using. Our global reanalysis is about 30-kilometer mesh horizontal resolution, but the regional one is at 2.5 kilometers. So, you know, much finer resolution, which means that then you can use better the observations and you can predict more finely what happens in all the different components of the Earth system. So now, what is the impact of observations, of different observations, on the quality of our forecasts, concentrating then on the Arctic? We have made some progress in assimilating different types of data for snow cover. So we always had synoptic observations, typical meteorological observations for snow, but we also use snow cover from satellite, reconstructed from satellite images, here the IMS product from NOAA. We've shown that this has an impact on snow analysis and snow forecasts. It also, interestingly, has an impact on atmospheric forecasts throughout the Northern Hemisphere. And in particular, these are examples of benefits. But when it's negative, it means you decrease the error for the low-level humidity or the temperature at low levels. So it's not just for the snow that we analyze the snow, and not just for the snow forecast, but really it helps for all our forecasts up to 10 days ahead there. And we know it's quite important for seasonal forecasts as well. In the year of polar prediction, we run different experiments together with partners in the context of the EU project Applicate here. We wanted to learn what was the importance of Arctic observations to improve the Arctic, but also how important were they for global forecasts. So for different seasons, winter and summer, we actually removed the data north of 60 north. We did it data type by data type. So all conventional observations, so weather balloons, synoptic observations, etc. Then all microwave, all infrared, all aircraft, etc. What we've shown is that in winter, it's really the conventional observations, so such as radio zones, which have the largest impact. You can see with the colors the change they make in the forecast error 3 days later, if you remove the radio zones. And these are closely followed by microwave observations and other data types. On the other hand, in summer, it is really the microwave observations which are by far the most prominent in terms of influencing data quality. And of course, it's true over the Arctic, but also over the Northern Hemisphere. So why is it different in summer and in winter? That's because in winter, we don't use microwave observations as much as we should, because over snow-covered or ice-covered areas, it is more difficult for us to extract the signal from microwave observations that are sensitive to the ground because of uncertainties in our temperature over snow and also on snow emissivity. So this led us to think that in our new strategy, in our new developments, we really have to learn how to better use microwave observations, in particular over snow and sea ice. And this is what we are going to do in partnership with Space Agency in particular, and we participated to a few workshops, both with EUMETSAT and ESA. And in our new strategy, our new 10-year strategy, we want to use observations in all sky situations, clear, cloudy, and all surface situations over ocean, sea, and snow. So what can we do to improve the use of polar observations over snow and sea ice? Well, we've developed an approach where we can actually analyze the skin temperature together with the data, which then helps to have a good lower boundary condition in order to use these microwave observations. And we could demonstrate in a very new experiments that this indeed helps in terms of weather forecasts in the Arctic if we use this better estimate of the skin temperature. For emissivity, it's also very complicated. This emissivity over snow and sea ice is not simple. Over the ocean, we use a model. We have a good model for emissivity. Over land, we use usually a retrieval or an atlas. But over snow, it's a bit more complicated. So what we are doing now is trying to use a radiative transfer model interfacing with a multi-layer snow model. For the time being, in our operational model, we only have one layer representing snow, but we're going to go to multi-layer, which is absolutely essential. So we worked in particular on this CMEM model together with ESA, and now we are testing this multi-layer snow radiative transfer scheme in collaboration with Japan. This is at 2 different frequencies, how we managed to simulate the observations. Here they are from ESA-ESRIN. These are the brightness temperatures in pink for different days in January 2019. And our simulations by the model should be quite close to the pink. And what you can see is that 10 gigahertz, the red dots, which is when we use the proper radiative transfer model for snow, are indeed good at reproducing the data. But at 89 gigahertz, they are not good enough. And actually, using an atlas is still better than using a more sophisticated radiative transfer model. So we are progressing on that, and we are putting a lot of effort on trying to analyze better surface temperature in case of snow and sea ice and emissivity so that we better use, in particular, the microwave data over these snow and sea ice covered areas. Now, we also try to use CryoSat products in terms of sea ice thickness. It's a product from Alfred Wegener Institute. We tried to insert that as a starting point of our seasonal forecast. And we could see that there was a good impact on, in particular, the areas of the 2-meter temperature for the September, October, November forecast initialized in May. So as you can see, it's a long-range forecast now. We're not talking about the next few days anymore. And we are talking here about the influence of sea ice thickness. So these results are quite encouraging. It was, although not always so positive, this was a good case, but sometimes when you initialize at different periods of the years, we still have a bit of degradation. So we have to understand it better before implementing this. Now, going to climate monitoring, I had shown you before an example of these reanalyses in general, but there are plenty of climate data records which are provided through our Copernicus climate data store. And in particular, here you can see some example of the mass balance of the Greenland ice sheet in terms of cumulative mass change, but also sea level contribution. So all this, of course, is being documented by satellite data and in particular CryoSat. So this is how sea ice in polar regions is based on satellite observation. So we have different products, sea ice concentration, sea ice thickness, where we use CryoSat 2, sea ice age, sea ice type. All this is very, very important for climate change. In terms of ice sheets, we also document the surface elevation change, and then we use CryoSat 2. We also use, going beyond the Arctic, we also use CryoSat 2 in terms of sea level anomaly. So now I will reach the conclusions of this talk. So it was a bit of a patchwork of what we do in general. I think I stressed the importance of the impact of satellite observations in numerical Earth system weather prediction. As I said, we have more than 95% of our data coming from satellite. They have a huge influence, but they're also, of course, essential for climate monitoring. There is a global importance of the polar regions in terms of climate, in terms of weather as well. So it really makes sense to make a special effort in analyzing and forecasting the polar regions. But we have some challenges in terms of using the data over snow and sea ice, which is what we are trying to tackle in our new strategy. When we go closer to CryoSat, then we are using ocean and sea state products operationally for forecasts at all ranges from the first few days to a few weeks and a few seasons ahead. And research has shown some positive impact of sea ice products for long-range forecasts, which we are not yet using operationally. And CryoSat is also very important for climate monitoring for a huge number of climate data records. So very happy at ECMWF to benefit from CryoSat and all this fantastic satellite data that help us to monitor the climate and also to forecast the weather. And thank you.
Thank you very much, Dr. Rabier, for this comprehensive presentation and showing how CryoSat is becoming a key element of SMWF modeling facilities. So now, please let me introduce the next speaker, Michael Mann, who will give a high-level overview of the EU space program for the Arctic. Michael Mann is EU Special Envoy for Arctic Measures since April 2020, and has previously served as EU Ambassador to Iceland. Since taking up duties, he has initiated, among other things, a public call for the revision of the EU Arctic policy, which is particularly instrumental in preparation to future Polar Sentinel expansion missions, including Crystal, which will largely build on the heritage of the CryoSat mission. So please, Michael, you can start.
Thank you very much indeed. Ladies and gentlemen, thanks very much for asking me to speak at today's conference. I must say it's slightly humbling to be among so many experts on the science of the Arctic and of space, but I will do my best to give you my view of the importance of space technology from the perspective of an Arctic policymaker. As some of you will know, the European External Action Service and the European Commission are currently working on an updated EU policy framework for the Arctic. Since the very start of the process, it's been clear that space will play an important and expanded role in our new policy. With that thought in mind, I would like today to set out the many ways in which the EU space systems Copernicus and Galileo are already playing a pivotal role in the Arctic. I will also explain how the EU will continue investing to enhance its space capabilities going forward, and how these improved capabilities will benefit the Arctic, both directly through improved connectivity and indirectly through better monitoring of the impact of climate change on the broader Arctic environment. When we think of science and technology and the Arctic, it's important to underline the importance of space research and what we know space technologies can deliver in a region so devoid of ground infrastructure. The EU clearly understands the role that space technologies have to play in the Arctic. The proof of that can be found in the European Union's 2016 space strategy and in the regulatory framework which will facilitate EU funding for the next 7 years up to 2027, both of which acknowledge the importance of the polar regions for the EU. Let us also not forget that EU space systems are already operational and are global in reach. They are already playing a vital role for the Arctic in helping us to understand climate change and in supporting transport safety and mobility. In particular, the current Copernicus polar activities serve the EU's political priorities in terms of climate action, maritime surveillance, exploitation of marine resources, energy, and the blue economy at large, biodiversity conservation, and cultural heritage. Planned enhanced Earth observation capabilities are also crucial for understanding the impact of climate change in the Arctic Ocean, Antarctica, and in Greenland. While the current situation is very much a reason for satisfaction, I also want to look at the great potential that we see for the future. As shipping through the northern passages increases, there will be an increased need also to continuously monitor moving sea ice and icebergs via Copernicus, and from there to help ships navigate safely away from danger using Galileo. At the same time, there will be a continuous need to inform ships about safe routings via secure communication channels. The European Union is currently looking to develop a multi-orbital satellite system which will deliver global service broadband capability. This will greatly improve connectivity in the Arctic, which is very, very poor in some regions. As you can see, we are forever developing our space systems with the user in mind. We are looking at the various ways in which communities and businesses in the Arctic can avail themselves of our space services and are taking action accordingly. Our space technologies are also well positioned to support broader EU political priorities, some of which are extremely relevant for the Arctic. Foremost among these is, of course, the European Green Deal, our concerted push for a more sustainable future and to make Europe the first carbon neutral continent by 2050. What's more, we are investing in new Earth observation missions, which are also highly relevant to the Arctic. These missions will help the global scientific community to better understand the environmental impacts of climate change in the Arctic, notably the impact on the cryosphere. Dedicated missions will provide vastly improved measurements of greenhouse gas emissions, such as CO2 and methane. Now, before I conclude, please allow me to focus now on Copernicus. Over the last few years, with the objective of supporting ESA in its technical activities to design future missions, the European Commission has carried out a number of initiatives to collect user requirements and to translate them into Earth observation needs for services and data for the polar regions. The Copernicus Polar Expert Group's work, in particular, has made an important contribution to the Copernicus programme. The findings in the PEGS report are timely and well elaborated, based on useful intelligence gathered from the Copernicus services and external scientists. This has not only ensured that the requirements of the user communities in the Arctic are understood, it's also laid the groundwork for defining an operational Copernicus polar observing system that's best suited to support the implementation of the Arctic policy overall, as well as the fight against climate change. Importantly, it places the EU and the European space sector at the heart of this fight. This has also helped to define potential new satellite missions relevant to the Arctic. ESA is currently assessing 6 new satellite missions, of which 3 could have a clear value for the Arctic. The Copernicus Imaging Microwave Radiometer mission, the Copernicus Polar Ice and Snow Topography Altimeter mission, and the Radar Observing System for Europe at L-band. Through the comprehensive work of the PEG, the Commission is well aware of the risk of potential gaps in Arctic data coverage and the impact such gaps would have on the quality and continuity of Copernicus services and products. Together with ESA, the Commission will continue its efforts to improve Earth observation capabilities in the Arctic in response to the observation requirements of users of Copernicus services and of researchers. The eventual Copernicus architecture responding to the EU's new Arctic policy, including the deployment of Sentinel expansions missions, will be agreed between the EU and ESA in the second half of 2021. The second half of this year will also see the publication of our new Arctic policy, on which we're now working extremely hard, and hopefully it will be published in October. You can rest assured that space technology will play a major role in bringing our Arctic policy up to date and making it fit for purpose. I want to thank you very much for listening and wish you the very best for today's event. Thank you.
Thank you very much, Michael, for this talk. Now I will introduce the next speaker with Dr. Sophie Nowicki, which will present about ice sheets and sea level projection, challenge and opportunities. Dr. Nowicki is a professor in the Department of Geology and Renew at University at Buffalo. Her main research focus is on Greenland and Antarctic ice sheets, their connection to Earth's climate system, and their impact on sea level, all topic particularly relevant at the light of CryoSat mission objectives. So please, Sophie, you can start.
Thank you so much. I hope you can see my screen properly. And if you can, then the picture in the middle is a picture that I like very much. As you can see, there is a birthday cake because it is an anniversary conference. You have my grandmother and you have my kids that are jumping for joy. They're not jumping for joy because sea level is rising, even though they know this is my type of work in the projections. But they are jumping for joy because we're about to eat cake to celebrate the 105th anniversary of my grandmother's birth. So the time scale, 100 years time scale, sometime seems so far away in terms of projections, right? The IPCC time scales, but really it's 3 generations. And so if you dig a bit more, the picture on the left is a map of what Antarctica looked like when my grandmother was born. You can see it's quite different than the map on the right, which is what Antarctica is according to CryoSat 2 when my kids were born. So without further ado, let's think about how do we make projections for IPCC. If we, sorry, this is where my, okay, great. The way that projections and the IPCC cycle for 100 years projections, I really made some of those assessments. And so the first and second and third assessment reports of the IPCC had a consistent message that basically we knew everything about the polar regions and the ice sheets. We didn't expect any dynamic changes for the 21st century, and the major contributor of sea level rise was thermal expansion and the melting of glaciers. Great, so we know everything. However, this story changed a lot for the fourth assessment report. One of the key reports and key statement was due to the observations of rapid change made over the polar regions that showed that there are very rapid observations over the polar regions actually. And so it would mean that a previous understanding of the behavior of ice sheets would need to be revisited. And this statement, understanding of this aspect, those rapid dynamical changes in ice flow that are being observed, is too limited to assess the likelihood or provide best estimate for the upper bound of sea level rise. And so in the space of a few assessment reports, we went from we know everything to we know nothing. And so this is kind of nicely reflected in the image that I'm showing, where basically it is the projections from the different assessment reports. You can see that in the beginning, Greenland was dominating the contribution, projected contribution with a potential rise, whereas Antarctica would actually lead to a sea level drop. This kind of story continued from until the third assessment report. In the fourth assessment report, this is when we start including dynamic in ice sheet models a little bit, not as well because we're being criticized, right? Remember that? But basically we start trying to kind of decompose the signal due to the climate forcing and the dynamic response of the ice sheets. And those are the things that the line that I hashed is basically the dynamic contribution. And so now we see that the contribution of Antarctica can actually lead to a sea level rise or a sea level drop. So we went from we know nothing, and this is when I was starting my PhD with Duncan Wingham, and I remember very well him showing images of like rapid change over Pine Island Glacier, to basically the next assessment report, right? So between AR4 and AR5, it really pushed the community to move forward and improve our models. Did that reflect in the assessment report? Well, a little bit. It was recognized that the projections of sea level rise are larger than the AR4, primarily because of improved modeling of land ice contribution. However, significant uncertainty do remain, particularly related to the magnitude of rate of this ice sheet contribution for the 21st century and beyond. So we are back to now we know something, but not enough. And you can see that again in those projections of future sea level contribution. Now we know that we are going to be having a future sea level rise in the 21st century. The diamond is basically the mean of the Greenland and Antarctic contribution, We also know that the Antarctic dynamic contribution is increasing, and that's something we need to watch out for. Okay, well, AR5 was in 2013, and as you know, AR6 is about to arrive. But what happened is that as soon as AR5 was published, the ice sheet modeling community kind of stuck again to this message that we know something, but still not enough. And so as a community, we created this ice sheet model intercomparison project for ESMID-6, which I had the chance to co-lead. We got established in July 2014, and we became a targeted activity of CLIC in order to address cryosphere in a changing climate and the future sea level contribution challenge for the WCRP. Our aim was to provide a framework to try to link the ice sheet modeling community with the climate modeling community in order to improve our projections of future sea level that could be considered and valuable perhaps to the IPCC AR6 assessment. It brought together two existing communities of ice sheet modelers, CRISE, which was a European, an American community led by myself again, and Bob Binschneider, and then the Ice2Sea, which was an amazing a European effort. So those two communities, you can see them in that figure, in that photo, some of the key players. But what is also cool about that photo that we took in the first workshop is that for the first time, we're also trying to include ice sheet modelers talking to observationalists because of the realization that observations are really key to our modeling. There is so much to say about ESMID-6. I'm not going to bore you to death about this, but basically at the bottom of my slide, I have some of the key papers that describe the protocols, and we spend a lot of time trying to select models for our projections as drivers of our projections. We spend years developing better forcing, and in particular, a strong focus on ocean forcing for the ice sheets. Because the challenge is that the climate models generally do not go into the fjords of the Greenland ice sheets, or they do not go beneath the ice shelves in Antarctica. And so we really need to improve those based on observations, of course. So in terms of projections, this is what you will get from ESMID-6. It's kind of the first image compares how the difference between model CMIP-driven, CMIP-6-driven, so like the latest generation of climate model, versus a selection of CMIP-5-driven, so the models that fed the AR5. The range that we have in the CMIP-5 models is in this box. And you can see that in general for Greenland, the sea level contribution are much higher if you use the latest generation of climate model to drive our ice sheets model. This is because, in general, those climate models have a higher climate sensitivity, and they also show more warming over the Greenland ice sheets. What is interesting, though, that's not really shown as well in this image, but in general, the behavior of the ice sheet model is quite consistent within one force from different climate models. And so the key takeaway message from those studies is really to improve our projections. We need to be at a stage where we need to improve the climate forcing and our understanding of the polar regions. The figure on the right, and the other figure with a beautiful PDF, is a way to kind of move the modeling field forward. We basically are taking all of the 256 simulations that the Greenland ice sheets that the ESMID-6 community made using 13 participating ice sheet model, 5 CMIP-5 models, climate models as drivers, 4 CMIP-6 models as drivers. So those to kind of expand this range of projections using emulators. That's a novel technique for the M-sheet community because basically it takes a long time to do simulations. And so if you want to translate something from one type of scenario, investigate different futures, emulators are very important. A point I will come back to is the NDCs. Those are the current emission pledges from our governments. And one of the things that you do see for the Greenland ice sheet is that as the temperature will rise depending on the future sea levels, depending on the future scenarios that we will face. So the difference, and those are represented with the SSPs. So from green to dark red means higher emission scenarios. Of course, the Greenland ice sheet is going to lead to more sea level rise. But for Antarctica, it's more tricky. We find from ice sheet modeling, the same type of model and experiments, then that there are huge differences in the way that the ice sheet is going to respond to those climate forcing. One of them, and that's one my first plot with my error bars and my box plots in purple. So you can see that depending on the choice of climate model will give you a different type of projections. Sometimes both the West Antarctic ice sheets and the East Antarctic ice sheets lose mass in a warming world, which makes sense. But other times you have, for like with the yellow model, you have this balance where you have some mass loss expected to the West Antarctic ice sheets, but you can also have a mass gain over East Antarctica because of more snowfall projected by this model. So Antarctica remains extremely tricky, not only because of the ice sheet models themselves, but because of the climate forcing. Because when a mass loss, those mass loss and those mass gains are two big numbers, and so they can cancel each other out. Another way to look at this same message, is my upper panels that shows that for West Antarctica and East Antarctica, 3 different climate models that are used to force those 14 or 13 ice sheet models on the different scenarios. At the bottom, it shows the sea level contribution for a low emission scenario. On the y-axis, it is a sea level contribution under the high emission scenario. And so you could expect that a your naive understanding, not your common understanding, my common expectation would be that in a warming world, you would have more mass loss due to higher emissions. But it's not necessarily the case. And that's something that we need to investigate deeper. We need to ask those questions. Are those drivers of ice sheet change that are driving those projections, are they drivers that we should use? Or is there some issues with those models? You can also see basically this complex picture of how Antarctica could react in those different emission scenarios. And now I'm looking at the bottom panels, where again I show those the result from the emulator, where you see that here in the warming world, from going from green to dark red, you do have the PDF, those curves are changing slightly in a warming world, but not that much. And so that's kind of puzzling for us. In East Antarctica, it is the reverse to some extent. Sometimes you basically have, again, a little shift in one way. But the thing that makes it very hard for projections is that you can imagine I'm adding those 2 big numbers. And so West Antarctica is often screwed a little bit one way under a warming world. East Antarctica is a bit screwed under the other way. And so because of basically more snowfall, the potential of more snowfall, that's East Antarctica, versus, of course, more mass loss driven by oceans for West Antarctica. And so those 2 curves, even though they might shift with different emission scenarios, they might tend to actually cancel out or balance each other out. So Antarctica is still very messy. Observations play a key role in our projections. We use them as input to our models. Those are key boundary conditions, like the bedrock. We use them to, when we assimilate, a lot of the ice sheet models start by assimilating the ice sheet elevation and the velocities of the ice sheet to get the best present-day state. But we also use them to evaluate our models. And so those are 2 examples of how these MIP6 models compare with observations. The plot of volume against area is for the Greenland ice sheets. The diamonds are 2 different estimates from observation derives. So here's a key takeaway message for you. We use observations but it is very important to know what the uncertainty is in these observations. There is basically a big difference between those two numbers. And so as an ice sheet modeler, which number should I use? The good news is that most of our ice sheet models do fall within that range. And if you were looking at previous effort, we would be even more spread out. So in the recent years, we have increased our modeling capabilities to be able to reproduce better present day. If you now look at my two other more colorful plots, those are for Antarctica. Here I'm comparing thickness by the models compared to thickness from observations, or velocities from the models compared to velocity from observations. But you can see here another problem that we have when we try to use observations. Those are two observations of key variables. None of the models are able to perfectly match them. Often there is kind of a correlation. If a model is not that great at doing thickness change, it's usually better doing velocities. If it's really good at doing velocities, for example, let's say those dark green, those pinky, this pink and this little green here, then the thickness is not that great. So we have an issue right now, is that basically often the observations that we use come from different time periods or are not consistent with each other. And so therefore it becomes really hard for our models to know how to best use them. So it is still not clear which observations should be used if you are going to try to kind of score models to try to improve projections. Observations play key role in the development of parameterizations that we use for SNP6. The first image is the Observational Estimate that was in 2013. And then my other two plots are possible basal melt rate based on new parameterization that we developed. Those two parameterizations have something in common. They both rely extremely on the observations because we kind of sample the observations to calibrate the parameters needed into our observations. How we did the calibration differ, however, is the same data sets. The mean ant method kind of said, well, you know, if I'm going to try to reproduce the observations with my parameterization, I should take all of the observations together equally. That's what we call the mean ant method. If we're using the pig method, it means that, well, actually, you know what, when I do the average of all of the basal melt rates, and then we do that locally too, right? So it's a bit more complex than I'm describing. Then actually, I really want to capture better the high melting in Antarctica and Panel and glaciers. And so I'm going to extrapolate and use those calibrations and give them more weight for my basal melt rates. So those two methods use the same observations, it's just different assumptions. Those have a big role to play because depending on how you use one or the other, of course, your projection is going to differ a lot. And so you can have basically a huge difference in the basal melt rates and the projections that you get. So we really need to continue observations and modeling to improve the clarity of Antarctica's future. An even bigger role for observation, something that we are really challenging with is representing the recent past. That image with the curves is basically ice sheet change from SNP6 Greenland. We didn't tell them how to reach present day, we only told them how to do the future. And so you can see, and then the gray shaded is the observation, so EMB shaded, and then Mugino et al. You can see that we're struggling. Ideally, we would want all of our models to fall within those observations. This group here that's falling below, that's basically observation models that simulate. The issue that we have is that, you know, we have a simulation, the observations are for a given time period. 27, for example, 2007. But if you want to try to kind of use this knowledge to assimilate and then assume that this was the ice sheet in, you know, a few decades before, then of course you're going to start with the wrong mass to start with. We're also having issues with forcing to apply, like what do we need to apply in terms of ocean and atmospheric drivers to drive a change. But there is some hope, and this is where the observation play a role. I'm showing you the composition of altimetry into surface mass balance and dynamics for different years. And this kind of observation is really fundamental, and we need more of those. Because the surface mass balance component tells me whether my climate models that I'm using are actually the right one. The dynamic response tells me whether my ice sheet model response to those forcing, or what I don't know, for example, the ocean forcing, is actually correct. An even bigger role for observations, you're going to start hearing a lot about calibrated projections. This is when we do tons of simulations because we don't know some parameters, and then to reduce uncertainty, we use observations. We basically give more weights to observations to model output that can reproduce the observations. And so for this example, for the MS&C sector, if I had used all of the observations, I would have had the gray bars. But if I use calibrated ensembles, one that basically gives more weight to observations that can reproduce the observations, then basically I reduced uncertainty in the outliers. I kind of kick them out. So in conclusion, hesitancy level, challenges and opportunities. Observations always drive model development. This is how we see things and then we implement them in models. They do play roles in projections right now, but we can play an even more greater role. I've shown you there is a big uncertainty in our projections. Observations will be key to reduce that uncertainty. For this, we need continuity in observations. Long records are really fundamental to reduce uncertainty. Model and observations are intertwined. You need the models to explain the observations. You need observations to know what observations are. Our community is developing new methods to make the most of observations and vice versa. As a modeler, it's sometimes really hard to know which observation I should use and how to best to use them. And as a community, we need to improve. And so if you're interested to join the MEP6 community, we're organizing a full workshop in 2021 that will be focusing on observations and how to improve the recent past. And so with this, I will thank the MEP6 community and give you a way to contact us if you want to join us.
Thank you very much, Sophie, for this very nice presentation, further underlying how important, even fundamental, is to observe the polar region, especially in support to climate projection. So now, last but not least, it is a pleasure for me to introduce our last speaker, who is Professor Andrew Shepherd, even if I assume that most of CryoSat family and friends already know him. So Andrew is Professor of Earth Observation at the University of Leeds, Director of CEPOM and Scientific Advisor to the CryoSat mission. His main contribution to science have involved developing remote observation of the cryosphere with a particular emphasis on polar altimetry and the CryoSat, for which Andrew will present an overview of key science results obtained over the last decades. Please, Andrew, the floor is yours.
Thank you, Jerome. Can you see my slides? Perfect. Okay. Well, thanks very much for inviting me to give this talk. I really love giving these talks. I'm sure anybody that's seen me speak before can probably tell that, because CryoSat really builds on a huge amount of work from lots of friends and colleagues who I've worked with over the years. So most of the work in here isn't my own. It's part of a team effort. I'll try to report as much as I can in terms of the headlines, but a lot of it is based upon the work that's emerged from the centre that I now direct and that originally worked in under Duncan Wingham, who, as we've already heard in the chat, conceived the mission a long time ago now. So I'll try and go back to the early days as well. So there's a cast list here of all the people that I think I should name check in this presentation. Lots and lots of great colleagues who've done amazing stuff with CryoSat over the years, helped us either in terms of processing the data, getting projects off the ground, or interpreting the science that's emerging from the measurements, and then making use of those observations to, as we've just heard from Sophie, for example, improve predictions for the future. So I want to thank all of these people, but I want to thank these people in particular, the women scientists, who are not just amazing scientists, but are amazing role models as well. And without their contribution, this wouldn't have been possible either. So thanks very much to you guys and girls. So I'm going to start with a slide that I put together recently based upon this really wonderful science art that Jill Pelto created for a front cover of Time magazine a couple of years ago now. And this isn't just a pretty picture, this is data at the heart of the image. from the iconic records of climate change that we've all become familiar with over the past 10, 20 or 30 years. So the obvious one are CO2 emissions that have risen since the 1880s from less than 300 parts per million to over 400 now, and have risen certainly for the past century. The global temperature has risen at the same rate. We all know this. And sea level has risen at the same rate as well. But what hasn't risen at the same rate is ice losses. And that's where CryoSat comes in. There's been an acceleration of ice losses in the past 10 or 20 years. And that's important because there's a lag time in the cryosphere to the changes in the global temperature induced by changes in emissions. And we're living through that period now, and we weren't living through it in the 1990s, Sophie has already pointed out. The good news story is that renewable energy is on the increase as well, but it's not increasing at the same pace as ice loss. So ice losses from Antarctica and Greenland are about 5 or 6 times higher than they were in the 1990s. Renewable energy use in the UK is about 4 times higher, and we're one of the global leaders. So there's work to be done around the climate system to try and mitigate the changes that are underway. And I want to take you back to the 1990s. This is the 1990s when CryoSat was first conceived by people older than I. I was just a postdoc in those days. And the world was a very different world then. There's some great tracks here, by the way. Some of my favorites are coming up later on. But the second IPCC report, as Sophie's already shown us, had a very, very different view of climate change to the one that you're probably familiar with now. And so there were a couple of figures about observations of changes in the cryosphere in particular. And the only one of note back in the 1990s was polar ice loss in the Arctic Ocean. And there was a sniff of retreat of Arctic sea ice back in those days. And it's quite remarkable to think that CryoSat was conceived and launched as an essential mission, as an Earth Explorer mission, when the world didn't believe that the polar regions would respond to climate change. So we've got a lot of people to thank for pressing that case, actually, not just developing the sensor, but pressing the case before there was a body of evidence to really convince people that change was under the way. We know that is definitely the case now. There are a couple of really iconic examples of climate change. Retreat of sea ice in the Arctic Ocean is one of them, and that is now absolutely demonstrable. Even back in the 1990s, there was a sniff of it, but it wasn't clear. 10% per decade reduction in Arctic sea ice, but also collapse of ice shelves at the Antarctic Peninsula. And we've seen a succession of those fall by the wayside over the past 20 or 30 years, a domino effect from the northern tip of the Antarctic Peninsula. This is Principal Staff Channel, which you can now sail through. Didn't used to be able to do that. It was an ice shelf covering the ocean between the Channel and Ross Island off the coast from the Antarctic Peninsula. And this is a record of abrupt climate change. So progressively, these ice shelves have disintegrated, and you can see that in the historical satellite records, and are no longer present. We can do good science, actually, as a consequence of them not being there. And if you take a look at the marine sediments that are on the seabed, you can date the provenance of different organisms, and that will give you a proxy record for the age of the ice shelves. And these have been around in the Earth's climate system for 10,000 years, and yet they've disintegrated in the past 20 or so. So this is an abrupt change, and it's an indication that abrupt changes can and do happen. And the cryosphere is actually one of the most important barometers for that, even though CryoSat was launched, designed actually, and launched before this was fully appreciated. So this is CryoSat 2 going up successfully in 2010. And it's not the most earth-shattering measurement concept, even though the radar is incredibly sophisticated. It's just sending a satellite over the polar regions. If you want to monitor the polar regions, you need a satellite that goes over them. That's the really basic rule. And we have a lot of satellite altimeters in space, but we only have 1, 2 now, thanks to IceSat-2, that are flying over areas where we see the dramatic changes. And we need that to continue into the future. But of course, CryoSat has really powerful radar that's able to see fine spatial detail that allows us to track lots and lots of different features of the cryosphere over time. And I want to run through a roll call of them now, of the main types of observation that we've managed to collect over the years from CryoSat. So the first one is the shape. We've already seen this, of the Antarctic ice sheet in this example. A couple of different studies have reported elevation models of Antarctica. really beautiful detail. And these are often the boundary conditions for numerical models or assessments of the total amount of ice stored in the continent, and lots of other properties of the ice sheet and glacier drainage systems all depend upon the shape of the ice sheet. But you can also see other features, the ice shelves, the glacial Lake Vostok, for instance, and the ice divides that separate the different parts of the continent. There's real glaciology in satellite altimeter measurements, and most glaciologists will tell you that it's a beautifully rich data set. We are also able to track changes in height over time. So this is an example. Many different people have done this over the years. It's now one of the most important records of changing mass in the cryosphere, thanks to its immediate representation of the changes of dynamic origin. You can see that here, the red areas over in West Antarctica are the progressive spreading inland of dynamic imbalance across the continent in that sector. We see singles elsewhere. We can measure the thickness changes of the ice shelves that fringe around Antarctica. Why is that important? Not just because they're collapsing. This is Sushil Dusamili's work along with Helen Fricker, but because they're melting from beneath. The ocean is, it turns out, the energy source for imbalance in Antarctica. The atmosphere is too cold to cause real damage. The ocean delivers huge amounts of heat, and that's eroding the ice sheet, nibbling away at the ice sheet around many hundreds or thousands of kilometers in the western sector, Bellingshausen and Amundsen Sea. And that's the area where we'll be concerned for the future. And you can see the effect of that. This is the grounding line, which you can map with CryoSat as well. The retreat rate at the edge of the ice sheet. This is the junction between ice and the ocean and the bedrock on the sea floor. And the areas of rapid retreat are in West Antarctica. And if we drop on a map of the ocean temperature anomaly, you can see why. The ocean is hot around this side of the continent and cold elsewhere relatively. And so this is where the heat supply is and the heat anomaly is, and the ice sheet's retreating as a consequence. The grounding line is actually one of the first places to change if we destabilize an ice sheet, and tracking a capability to track the grounding line is really going to be an early warning system for future dynamical change. We can see subglacial lakes. There's lots of studies. Matt Siegfried and Helen Fricker and others have looked at the distribution of subglacial lakes. These are lakes beneath a kilometer, 2 kilometers, 3 kilometers of ice, and we can detect their presence because of changes in the surface above them as a consequence of water moving around between networks of lakes on the ice sheet base. And in Greenland in particular, we can see wonderful separation. Sophie showed an example of this between the elevation changes, the ice thickness changes that are due to glacier dynamics on the right, and changes in surface melting in the center. So the signal from CryoSat is on the left, and it's a composition of these two processes. And they each require representation in numerical models, and they each have different pathways for future climate evolution. And it's important to be able to separate the two out. And if you can rely on the models to do that, the middle example is one of these, then you can retrieve the dynamical instability on the right-hand side from the altimetry data alone. You don't need ice velocity measurements. And this is a really powerful separation of the processes that are going on. Again, this is glaciology in action. One of the really exciting things for me has been developing the mission capability. So this is the standard elevation on the left-hand side and elevation change measurement on the right-hand side from CryoSat's synthetic aperture radar interferometric altimeter. And Noel Gormel and colleagues, Livia Jacob and Paul Tepes and Luca Forrester have pioneered amongst other people, use of swath processing to fill in the gaps. And we now have a continuous measurement of elevation and elevation change in the interferometric mode areas that are covered by the ice, by the satellite. Sea ice, this is a beautiful composition of Arctic sea ice thickness, an example from measurements that Rachel Tilling produced originally. Seymour Laxon, as many of you know, was the first person to report changes in Arctic sea ice thickness from CryoSat, but many other teams have done that since, RV and JPL, among others. And we can now even measure the thickness of the snow layer on top of the sea ice using dual frequency altimetry, thanks to the fact that we've got or had Ka band measurements in space at the same time. So this is a couple of examples. This is Isabel Lawrence's example of changes in the seasonal changes in the thickness of the snow layer. That's really important, not just because it's a constraint or a limit on the precision with which we can measure sea ice thickness, but because it's an insulating layer on the sea ice itself, and it governs the longevity of first-year ice in particular. If you have a thick sea ice snow load, then it's a blanket, and the ice lasts longer through summer than it otherwise would do. We can measure the distribution and thickness of icebergs now. This is a nice animation Noel Gormelin produced, but other people, and Brackman Polgman, for example, are measuring changes in the distribution and thickness change of icebergs floating around in the polar oceans. And we can use CryoSat for many other things as well. This is Dave Sandwell's marine gravity anomaly map, which can be inverted to get the ocean thickness. And we can also look at dynamic ocean topography. This is around the southern oceans now, newly identified as an ocean by National Geographic. I don't know whether that counts as a genuine thing, but they think it's the sixth ocean. This is an example produced for the southern ocean of the ocean currents around Antarctica. And we can use it to track sea level change. So this is Remco Charoux's addition of CryoSat measurements to all the other ocean-going altimeters that are measuring the non-polar regions of our planet. I just want to touch on one assessment that we produced recently, because I think it's a really great example of CryoSat being able to survey the entire cryosphere, in effect. So this is Earth's changing cryosphere. Bits of it change visibly over time with the seasons. The bits on land and in the oceans, for instance, snow cover and the sea ice cover have a seasonal cycle that's really apparent because they change in extent. But the land ice in Greenland and Antarctica and the mountain glaciers is difficult to sense in optical imagery alone. And we need thickness measurements and charting of thickness measurements over time to track their evolution. So I'm going to go through stepwise the different components of the cryosphere and how we've assessed their changing mass with CryoSat and other satellite sensors. So I'll start with Antarctica, then I'll look at the ice shelves around Antarctica, Greenland, the mountain glaciers, and then the two sea ice regions. And just for scale, we'll drop this ice cube next to New York City to illustrate the scale of ice imbalance on our planet today. So this is a 10-kilometer base cube of ice, and that's how much 266 billion tons or gigatons of ice would look like next to Lower Manhattan. This is how much ice is lost from mountain glaciers each year, and the time variation on the right-hand side, Tom Slater's work and others. 166 gigatons, billion tons from Greenland, 111 billion tons from Antarctica, 284 billion tons from ice shelves, 329 billion tons from Arctic sea ice, and even over this time period, 40 billion tons of ice lost from Antarctic sea ice, which is bucking the trend that we've seen a modest increase over the past 30 or 40 years because of a sharp decline over the 2016-2017 seasons. And when we drop that onto the map of the planet, we can see the biggest losers are Antarctic ice shelves, in fact. So these parts of the cryosphere, which were not thought to be too important in the 1990s, turns out they're the biggest losers over our generation and are really important because they're the interface to the grounded ice that sits behind them and can cause sea level rise. When they melt or disintegrate, the glaciers behind them simply speed up and put more ice into the ocean. Arctic sea ice, the next biggest loser, really important, reflects less of the sun's heat into space, and we're warmer than we otherwise would be. So two really, really important elements of the cryosphere are battling it out to be the biggest losers in terms of ice. Mountain glaciers are still an important component of the ice loss overall, and then the Greenland ice sheet and the Antarctic ice sheets are following behind. Small on average over the past 30 years, but these are the two parts of the cryosphere that are showing accelerating trends, 5 to 6 times increase over the past 30 years, far outstripping the pace of increase in any other element of the climate system. And then even Antarctic sea ice has a contribution. What does that mean? Well, it means that we can expect some sea level rise, in particular from the polar ice sheets. And this is the changing sea level as a consequence of Greenland and Antarctic melting. CryoSat has become an integral part of this assessment. In the past, we had altimeters that covered parts of the polar regions of the Greenland and Antarctic ice sheets and were incomplete, and we relied upon other measurements. But CryoSat is now about a third of the measurements that go into our assessment of polar ice losses today, and it will continue to be really vital. What do we use it for? Sophie's already shown. This is a numerical model evolution of the Thwaites and Pine Island glaciers. It's one simulation over the next 300 years, produced by Steph Cornford. It's showing you a map of the ice speed, but also the aerial retreat of this glacier. And this glacier holds enough ice to cause a meter of sea level rise. So this is one of these extreme events from ensemble runs of numerical models, which are worrying people, low probability, high magnitude events, which could cause significant sea level rise. And we want to be able to have confidence in those model predictions. So as Sophie has shown, in the IPCC models over the past 30 years have changed quite dramatically. We've seen a progressive change from Antarctica gaining mass to now Antarctica losing mass. And the good news is that when we compare those models, the latest ones, they're the ones that agree closest with the satellite observations. CryoSat is quite close, so the models are, in fact, quite close to reality today, when we have known that in the past they haven't been close to reality. So this is a really good news story. The models have improved in fidelity in the observational period, and that gives us higher confidence that we can use them for predictions. And predictions are important. This is the county that I live in the UK. This is Yorkshire, and it's our coastline, and we love our coastline for lots of different reasons. Some people take their caravan holidays there. Lots of people in Britain will be doing that this summer because we can't get to anywhere else. We've become accustomed to coastal retreat in some parts of our country, but not others. And in the future, we'll have to accept managed retreat of our coastlines. We can't protect everywhere. These caravans will be lost. And it's as a consequence of sea level rise, not inundation that we've been led to believe over the past 20 or 30 years from different parts of the, I guess, climate skeptic lobbies. But because of the increased periodicity of high storm events, which cause the most significant erosion. So when sea level rise combines with high tides, we get more frequent flooding in coastal areas, and that nibbles away at our coastline and causes disruption to anybody that depends upon it. This is a good example of numerical model predictions, latest, as Sophie's already shown, from Tamsin Edwards, but also Rob DeConto has done the same. What we do is we throw out today the model realizations that don't fit, or we downweight the ones that don't fit the historical observations, and that gives us improved confidence in predictions for the future. So the measurements that we collect today are not just important for telling us what's changing, but they're really important for narrowing down the uncertainties on future sea level rise, which is really important for decision makers. And so this is an example of that. This is the satellite observations dropped onto the last IPCC assessment report's predictions for sea level rise. And the bad news is that the observations are not tracking that middle range scenario. They're tracking the upper range scenario, which allows for an extra 17 or 18 centimeters of sea level rise over the next century. On average, it will be higher in different parts of the planet because there's an uneven distribution of the sea level load, depending on where you live. And what does that mean? Well, every centimeter of sea level rise brings 2 to 3 million people per year into a situation of annual coastal flooding. So it's not insignificant. You might think that that number is small, but it isn't in terms of the impact it has around the planet. But also sea ice retreat has an impact on our climate. This is the beast from the east, a storm that hit Europe, but the UK in particular, and caused very, very cold temperatures, which people in Britain were not used to, minus 20 degrees centigrade. And our transport system basically ground to a halt, but it did it across Europe as well. And this, it turns out, was partly due to retreat of Arctic sea ice. So the exposure of the Barents Sea and Kara Seas as a consequence of Arctic sea ice retreat has allowed more water to evaporate from that part of the Arctic Ocean. And that's created wetter, moist air flows in northern Siberia. And that was the prime contributing factor towards this cold spell that came down from the Arctic and hit Northwest Europe. So changes in sea ice do matter to us. You might not think the Arctic is on our doorstep, but it is in terms of weather patterns. This is an example, improved sea ice prediction from the Met Office, but many other organizations are doing this now. Assimilating, we heard from Florence that the ECMWF are doing it too. Assimilating satellite observations, not just of extent, but also thickness, to update their predictions of Arctic change. And this is a difference in air temperature in the Arctic as a consequence of a simulation of the satellite measurements. It's actually 4 degrees cooler than the model thought it was. And that's thanks to including the sea ice thickness measurements from CryoSat into the Met Office model. So what about the future? We heard Tony talk about Crystal, and of course it is a selected mission. Money hasn't been committed 100% for it in the future, but this is the satellite that we'll depend upon in the future. So I'm grateful to Duncan and Richard and others who designed CryoSat before I even started as a polar scientist, and hopefully future polar scientists will be grateful to the people that are designing Crystal, which will be operating in the 2030s. So we've made use of non-polar satellite altimeters, ERS-1, ERS-2, the longest surviving altimeter ever, 17 years, ENVISAT, ICESat-1 and CryoSat-2, and now ICESat-2. These missions hopefully will live on until Crystal can be launched in around 2030. That still has to be 100% subscribed to. Hopefully that will be a decision taken towards the end of this year. So I want to summarize, hope I haven't gone too long. CryoSat's 11 years in space, so we have had a decade of polar altimetry thanks to CryoSat. Hopefully we'll have years more so that we won't have a gap between the golden age of observations we have today and those that we'll have in the future when we have a dedicated polar mission. The mission capability has been extended beyond what we expected thanks to the SWOT processing. It's now monitoring all elements of the cryosphere and improving climate model predictions. If you want to take away number, Earth is losing 1 trillion tons of ice per year. It's not a good news story, but it's good news in the fact that we are at least aware of this now, whereas we wouldn't have been without these satellite observations. And there's been a 6-fold increase in ice sheet loss, tracking the worst case scenario of the IPCC's last assessment report. The jury is still out in terms of the next report, which is due out in summer. Raises the annual flood risk to 400 million people. And it costs 2 euro cents per European citizen per year to be able to tell everybody this. So this is cheap at half the price, as we say in the UK. This is not an expensive mission. I really hope that we can find the cash within Europe to launch a successor, because it's not a high cost, but it's a really, really important observational data set. So I'll finish with some photos from the launch, actually, in particular, of me and some of my colleagues. You might see yourself on there. If you don't, I apologize. I don't have photographs. Apparently, we didn't take them in the 2010s. I didn't have a smartphone there. So thank you very much, and I'll end there.
Andy, thank you very much. I think I can echo Jerome's words in thanking all the speakers this afternoon, and I think the start of this conference, it's already very interesting, and I think we're all looking forward to the next sessions. Talking about sessions, we have now a coffee break. I think it's actually an extended coffee break, so I think the next session will start, Jerome, am I right, 3:30, is that correct?
Yes.
So 3:30, we will start with sea ice. I think it's the first session on sea ice, and I welcome the presenters of the next sessions to stay maybe during the coffee break and try to try the presentations. I think someone from the event coordination will be assisting you. So thank you very much, and looking forward for your next presentations. Thank you.